Welcome to Tomorrow Unveiled, the show where we take a stack of the latest insights and really try to boil them down to the essentials for you.
Get right to the core of it.
Exactly. And this week, our dedicated research team has pulled together this, remarkable cluster of signals. It really feels like a decisive global pivot in clean energy is happening. We're talking about a pretty fundamental shift, redefining how we power everything. We're calling it green code hot core.
Right, so the green code being that push for deep decarbonization.
Yeah, getting the emissions down. And then the hot core, that's the need for clean but also really dense, reliable 247 power.
And what's so interesting, looking at the research from this past week, June 26th to July 3rd, 2025, is that these aren't just, random news flashes.
Right.
It feels like a real convergence. Market demand polling, policy support pushing, especially for things like advanced nuclear fission and fusion, moving them out of the lab and towards actual commercial reality.
It really points towards a future where that reliable, concentrated clean energy is just foundational for industry, for AI's crazy power needs, everything.
Absolutely indispensable.
Okay, so let's unpack this for you. We're going to dive into the tech breakthroughs, the big shifts in money and policy, and, what it all might mean for a sustainable energy future. Sound good?
Let's do it.
All right, first up, something our research team flagged as genuinely historic. A major tech company making a direct power purchase agreement, a PPA, for commercial fusion energy.
Yeah.
You might have seen this one. Google's deal with Commonwealth Fusion Systems, CFS. Why is this specific agreement such a big deal?
Okay, so this Google CFS agreement, they're planning to buy 200 megawatts from CFS's first ARC plant, planned for Virginia, early 2030s.
200 megawatts of fusion power still sounds wild.
It does, but this is the key. It's not a research grant. It's a commercial contract. Google's saying, we will buy this product even though, the factory isn't fully built yet.
Right.
That massively de-risks things for CFS. It starts to set a real price point for fusion power. And it's driven by these huge constant power demands. Think AI data centers needing power all the time.
Nonstop. And Google didn't just sign a PPA, did they? The research mentioned more investment, too.
That's right. They also upped their equity stake in CFS. So they're putting their money where their mouth is, showing real confidence this tech can actually get to market. It's a huge vote of confidence.
So to deliver on this, CFS is banking heavily on its Spark project. What exactly is Spark, and what's the main thing it has to prove?
Okay, Spark. It's a tokamak, that donut shape using magnets to hold the super hot plasma.
Right.
But it's compact, much smaller. The goal is net energy gain and getting more energy out than you put in to heat the plasma. They're aiming for that around 2027.
And how are they making it smaller?
That's the innovation. Revolutionary high-temperature superconducting magnets. They create much stronger magnetic fields so you can confine the plasma effectively in a smaller space. That's the game changer.
So proving net energy gain with Spark is the key step.
Absolutely. That's the scientific hurdle. Once Spark works and proves the physics and the tech, the ARC power plant, the one Google's buying power from, is basically a scaled-up version, a direct blueprint.
Got it. And beyond just this commercial deal, our research also highlighted some incredible progress just in controlling the fusion plasma itself, which is, that's the fundamental challenge, right?
It really is.
Yeah.
And we saw big steps this week. South Korea's K-Star reactor, they hit a new world record plasma at 100 million degrees Celsius, held stable for 48 seconds.
48 seconds. That's huge progress.
It is. And it helps validate key ideas for the big international ITER project. Then you had TA Technologies publishing work on stable plasma that could mean simpler reactors down the line.
In Germany, too.
Yep, the Wendelstein 7X Stellarator, that's a different, twistier shape than a tokamak, also hit its own record. Over 20 million Celsius for 43 seconds.
So taken together, what does this tell us?
It tells us the science is maturing, fast. We're getting much better at achieving and, crucially, maintaining the extreme conditions needed for fusion. Stability, control, that's how you eventually harness the power. That hot core is definitely getting hotter, scientifically speaking.
Okay, let's shift gears slightly. From fusion's potential hot core to another realm of high-density energy, advanced fission, nuclear. Our research this week pointed to a major acceleration here, too.
Definitely. A real renaissance, you could say.
But what seemed interesting was this kind of two-track approach emerging globally. You have state-led efforts pushing for massive scale, especially in the East, and then more private-led modular innovation in the West. Is that a fair summary?
I think that captures it well. It's a pragmatic split. adapting to different contexts, and it's speeding things up everywhere.
So let's start small. Microreactors. The research highlighted a big step in the U.S.
Yeah, huge news. The Department of Energy, the DOE, picked two companies, Westinghouse and Radiant Nuclear, for the world's first fueled microreactor tests.
Fueled tests. So actually running them with nuclear fuel.
Yeah, exactly. At a new facility called DOME, out at Idaho National Laboratory. Testing starts potentially as early as spring 2026.
And what makes this dome facility so important?
It's a game changer because it's a shared, federally backed test site. It drastically cuts the cost and regulatory hassle for these companies, speeds up that whole path from design to actually getting something built and tested.
Makes sense. And tell us about these first two reactors, Westinghouse's.
Right. Westinghouse has the Avinci. Think of it like a nuclear battery. It's solid state, uses heat pipes, so no moving parts for cooling, generates about 5 megawatts electric, really targeting remote places, data centers, mines, maybe military bases.
And Radiant Nuclear.
Theirs is the Kaleidos, smaller, so at 1.2 megawatts electric. It's a high-temperature, gas-cooled design, and get this, it's designed to fit in a standard shipping container.
Wow, for portability.
Exactly. Think disaster relief, power and critical infrastructure quickly after an event. Very different use case.
Okay, so that's the micro scale. What about slightly larger, small modular reactors, SMRs, also seeing movement?
Big time. Global momentum. In the U.S., NuScale Power just got its second SMR design approved by the Nuclear Regulatory Commission. They're aiming for commercial deployment starting end of 2025. And their manufacturing partner, Doosan, is already gearing up to build like 12 modules a year.
So that's ramping up. And the UK?
The UK government picked Rolls-Royce SMR as its preferred partner. That's a bigger unit, 470 megawatts electric. They want the first ones on the grid by the mid-2030s, talking about thousands of jobs.
Okay, so that's the West. What about elsewhere? You mentioned state-led efforts.
Right. Look at the Nordic region. GE, Vernova Hitachi, is working with Finland's Fortum on pre-licensing for their BWRX 300 SMR, again, targeting the 2030s.
And China.
China's pushing ahead with ambitious plans, 10 gigawatts of thorium molten salt reactors by 2029. That's a different tech, potentially safer, uses liquid fuel. And China National Nuclear Corporation just hit a major construction milestone at Haiyang 4, one of their big CAP-1000 reactors. Keeps it on track for 2027 operation. Shows their speed.
10 gigawatts is a lot.
It is. And Russia isn't standing still either. Detailed plans for 4 new 600-megawatt reactors at Kola II, planned between 2027 and 2037. Designed for an 80-year life, aiming for a closed fuel cycle too.
So you really see that split, the West focusing on innovating and de-risking smaller modular designs, often private-led, while the East is state-driven, aiming for massive scale and efficiency.
Exactly. 2 different strategies, both pushing advanced nuclear forward.
But, you know, breakthroughs are great, but they don't happen in a vacuum. You need the money, you need the right rules.
Absolutely critical.
And our research team saw some really monumental shifts on that front this week, things that seem to be genuinely clearing the path for this high-density clean energy future.
You're hitting on maybe the most impactful developments, policy and finance. And one of the biggest, honestly, came from a place you might not expect. The World Bank.
The World Bank, what did they do?
Get this, on June 26, they officially ended a 65-year ban on financing nuclear energy projects.
65 years. Wow. Why now? What changed?
Our research points to sort of 3 main drivers converging. First, basic development reliable baseload power is key to lifting nations out of energy poverty. Second, it lines up with global climate goals, specifically that COP pledge to triple nuclear by 2050.
Right, that got a lot of headlines.
And third, it's geopolitical. It offers a transparent, multilateral financing option, an alternative to, say, state-owned companies from Russia or China dominating the nuclear market in developing countries.
So what kind of projects will they fund initially?
The focus seems to be on extending the life of existing safe reactors first, providing technical help to countries just starting to explore nuclear, and importantly, helping accelerate SMR deployment. SMRs are seen as potentially ideal for emerging economies, smaller upfront cost. Scalable.
Okay, World Bank, that's huge globally. What about domestically in the U.S.? Any moves there?
Definitely. The DOE is actively trying to streamline things, cutting red tape. They launched a pilot program aiming to fast-track construction and operation of at least 3 advanced reactors on private sites by July 2026.
Fast track, like really speed it up.
That's the goal. They're also updating environmental reviews, explicitly talking about ending permitting paralysis, trying to make the process faster and more predictable.
And there was that budget bill on the Senate, too. That sounded significant.
Hugely significant. A Republican-led bill past reconciliation. It signals a major shift in thinking about energy support.
How so?
Well, it starts to curtail or put end dates on some of the long-term tax credits for intermittent renewables like wind and solar. But, and this is key, it explicitly keeps incentives going through 2032 for firm, dispatchable, clean energy.
Firm and dispatchable, meaning?
Meaning power sources you can count on 24/7 that you can turn on when needed, like advanced nuclear, geothermal, hydropower with reservoirs. It's a move away from just supporting any low-carbon source towards valuing reliability and availability, a recognition of system needs.
That feels like a really fundamental policy evolution.
It is. And we're seeing big capital flowing, too. The UK government reaffirmed its commitment to large-scale nuclear, $14.2 billion, for the Sizewell C project. That's a big 3.2 gigawatt plant. They're using a model called RAB Regulated Asset Base to give investors more certainty.
And back in the U.S., Texas?
Yeah, that hypergrid project in Texas,
Yeah.
backed by former Energy Secretary Rick Perry.
The plan is wild. 11 gigawatts of mostly nuclear power on just 6,000 acres. They hope to get the first gigawatt online by 2026.
11 gigawatts on one site. That's immense density.
It really highlights the land use advantage.
Okay, this seems like a good moment to just pause and say, if you're finding this insightful, maybe learning something new, please take a second to like this video. If you're on YouTube, subscribe to Tomorrow Unveiled, and definitely hit that notification bell so you don't miss our future updates.
And if you're listening on Apple Podcasts or Spotify or wherever you get your audio, we'd be incredibly grateful if you could leave us a rating and maybe a quick review for Tomorrow Unveiled. It genuinely helps other people discover the show. It really does. Okay, so we've talked tech, policy, money, but what about sustainability in the broader sense? Beyond just, emissions during operation, the whole life cycle. Our research team dug into that too.
Yeah, that's vital. Can't ignore it. For fusion, the research shows a really low carbon footprint overall. Something like 9 grams of CO2 equivalent per kilowatt hour.
How does that compare?
Very favorably. It's in the same ballpark, maybe even better than traditional nuclear fission or wind power, actually. Most of that footprint is just the embodied carbon making the materials, construction.
Okay, low carbon. But the big question always with nuclear tech is waste. What about fusion waste?
That's one of fusion's biggest potential advantages. No high-level, long-lived radioactive waste like spent fuel from fission reactors.
Not at all.
The main radioactive waste comes from the reactor materials themselves getting activated by neutrons. But it's mostly low to intermediate level stuff.
Oh.
And crucially, it decays much, much faster. We're talking down to safe background levels within maybe 50 to 100 years.
Not thousands or tens of thousands of years.
Exactly. And there's a lot of research focused on developing low activation materials to minimize it even further, plus recycling strategies.
Okay, that's fusion. What about those microreactors we talked about? How do they handle waste?
Well, take the Westinghouse Vinci. The design itself is emissions-free, doesn't need water for cooling, tiny physical footprint. But the really interesting part is their business model, this nuclear battery idea.
Right.
The plan is the entire sealed reactor unit, including its used fuel inside, gets sent back to Westinghouse at the end of its life. They handle the centralized disposal or recycling.
So the user doesn't have to deal with waste on site.
Exactly. Simplifies things enormously for the customer and keeps the waste management centralized and controlled.
And beyond specific reactor designs, our research also picked up on innovations in the wider nuclear fuel cycle, addressing some of those long-standing challenges.
Yes, definitely. Really important developments there, too. For instance, South Korea KHNP, their utility just loaded the first demonstration assembly of their own domestically developed accident-tolerant fuel, or ATF.
Accident-tolerant fuel. What does that mean?
It means the fuel itself, the pellets, and the cladding around them are designed to withstand much higher temperatures and harsher conditions, like if cooling was lost in a severe accident. They maintain their integrity longer, giving operators more time to respond. It's a big safety enhancement.
Okay, that's significant. And recycling.
Yeah, a Canadian company, Moltex Energy, announced a breakthrough there. They have a process called Watts Waste to Stable Salt. They claim it can extract over 95% of those long-lived radioactive elements from used fuel.
Turning waste into fuel.
Essentially, yes. Transforming what we currently consider high-level waste into a valuable fuel source for certain types of advanced reactors. And they say it could cut the volume of waste needing permanent geologic disposal by as much as 80%.
80% reduction, wow.
And related to that, Argonne National Lab and a company called Curio Energy are also working on recycling tech, claiming they could cut high-level waste volumes by about 97%. So lots of action on the waste front.
And one more crucial piece for advanced reactors, the fuel itself, right? They don't all use standard reactor fuel.
Correct. Most advanced designs, including those microreactors going into the dome tests, need something called HALEU, high-assay, low-enriched uranium. It's enriched to a higher level than traditional fuel.
And is it available?
That was a bottleneck. But a key development this week. Centrus, a U.S. supplier, met its production target for HALEU for the DOE and got its contract extended. That's critical infrastructure for the whole advanced reactor industry.
So when you put all these pieces together, APF, recycling, HALEU production...
You see a maturing ecosystem. These things are interdependent. You can't run the advanced reactors without HALEU. Public acceptance is harder without addressing waste and safety through recycling and ATS. These aren't just technical nice-to-haves. They're vital for building the social license to operate.
Makes sense. And finally, on sustainability, just touching on land use again, that hypergrid project aiming for 11 gigawatts on 6,000 acres really stands out compared to the footprint of, say, solar or wind for the same capacity. Plus jobs, though, community acceptance is always key.
Absolutely. Density matters for land use, and these projects bring high-scale long-term jobs. But engaging with communities is non-negotiable.
Okay, so let's try and bring this all together. We're seeing this huge push towards high-density, hot core, energy fusion, advanced fission, but, solar and wind are still growing like crazy. So what does this actually mean for the bigger energy picture? Is it like high density instead of renewables? A zero-sum game?
That's the million-dollar question, isn't it? But connecting all the dots from this week's research, the analysis suggests it's more of a rebalancing of priorities, not really a replacement scenario.
Rebalancing.
Yeah. Look, intermittent renewables, solar and wind, they're not going away. Their growth is phenomenal. BRICS nations, for instance, now account for over half the world's solar generation. That continues.
But the policy winds are shifting, as we discussed, valuing different things now.
Absolutely. That U.S. Senate budget bill is maybe the clearest signal. Moving away from just subsidizing any low-carbon kilowatt hour towards valuing reliability, dispatchability. There's a growing recognition of the system costs that come with very high levels of intermittent power, needing backup, massive grid upgrades, storage.
So even if an SMR's cost per unit of energy looks higher on paper in some places,
Its value proposition is broader. It's not just about being carbon-free. It's about resilience against extreme weather. It's about fuel security, long-term price stability once it's built. Those attributes are getting valued more.
so it's not nuclear instead of renewables.
The research points strongly towards nuclear and renewables. Think about those massive 247 power demands we mentioned. Google's AI data centers needing guaranteed power, or the needs for industrializing developing nations reliably. Intermittent sources alone just can't meet that foundation.
So the hot core, the reliable nuclear fusion, actually enables more renewables.
Precisely. It provides that bedrock grid stability. That constant, reliable power allows the grid to handle even more variable wind and solar without falling over, without compromising the integrity of the whole system.
Ah, interesting.
And that Google PPA for fusion, it's a perfect commercial example. They are explicitly paying a premium, likely, for the attribute of reliability, for power that's guaranteed around the clock for their critical operations.
So the conversation is shifting.
Definitely. It's moving beyond just which tech makes the cheapest electron towards what's the right portfolio of technologies to build the most reliable, most resilient, and ultimately affordable energy system for society. It's a more sophisticated system-level view.
What a week. It really feels like this green code hot core idea is not just a concept anymore. It's actively shaping investment and policy.
The momentum is palpable,
Yeah.
driven by these incredible tech advances in fusion and advanced fission, yes, but just as much by these major shifts in global finance and national policies we've seen.
And the timelines seem to be accelerating. You mentioned fusion plants targeted for the early 2030s.
That's the aggressive target for pioneers like CFS, yeah. And SMRs aiming for grid connection in the mid-2030s in places like the UK. Those microreactors, with the dome testing starting soon. Initial deployments could be even sooner, maybe late 2020s for specific niche applications.
Of course, huge hurdles remain. Let's be realistic. Sustaining fusion power commercially is still an immense engineering challenge.
No doubt.
Regulatory pathways for all these new fission designs need to be navigated smoothly. And building and maintaining public trust, that social license.
Absolutely crucial, ongoing work.
Yeah.
But the direction of travel this week seems unmistakable. A profound shift is underway.
Which leads to a really interesting question, I think. As our world needs more and more energy, especially this always-on kind for AI, for electrification,
Yeah.
how do we collectively decide to prioritize those different energy attributes?
Right. The cost, the reliability, the sustainability across the whole life cycle, the security. How do we weigh those factors as we build the global power system for the rest of this century?
That is definitely something for all of us, for you listening, to mull over. A lot to think about there. Thank you for joining us on Tomorrow Unveiled.
Always a pleasure.
And we genuinely love hearing your thoughts. So whether you're watching on YouTube or listening on your favorite podcast app, please drop a comment. Let us know what you think about these energy advancements, about this green code hot core shift we've been discussing.
Now, what's your take?
And one last time, if you enjoyed this discussion, please think about subscribing to Tomorrow Unveiled. And if you're on audio, leaving that rating or review really does make a difference for us.
It helps us keep doing this.
It does. We'll see you next time as we continue to unveil tomorrow today.